Hi, I selected project type 1 and chose a dim learning paper to re-implement. I'd like to introduce the evolution of image super resolution. First, I provide the definition of image super resolution, and then I give an overview of its progression over time. I re-implemented a total of 3 papers. I talk about each of the 3 models, and then I present the result of applying the actual images to the model. Single image super resolution is a branch of computer vision research and a classical problem. It is a technique for generating high resolution images from low resolution images. Before the introduction of deep learning in 2015, there were methods such as bicubic interpolation and linear mapping that were used for single image super resolution. However, since it is based on a relatively simple linear mapping, it has a problem that it is difficult to implement a complex and non-linear model. To solve this problem, a deep learning-based super-resolution algorithm has been studied in various ways using convolutional neural networks. In other words, it is learning of filter parameters that can convert a complex non-linear relationship between low-resolution input and high-resolution output. This figure shows the order of appearance of image super-resolution models using deep learning over time. It first appeared in 2015, and since then numerous models have appeared. Among these numerous models, I implemented 3 models. The Super Resolution Convolutional Neural Network, which introduced deep learning for the first time, the Fast Super Resolution Convolutional Neural Network, which was lightweight, and finally, the Enhanced Deep Residual Network using residual learning. The model of the first paper is SRCNN. It was announced in 2015 and applied deep learning-based CNN for the first time. It was one integrated network and used an image upsampled by interpolation as input. SRCNN has 3 relatively simple convolutional layers, and this paper analyzed the role of each layer in terms of traditional super resolution techniques. The first layer is a convolutional layer that extracts patches from low-resolution images and expresses them in feature map units. The second layer is a convolutional layer that non-linearly maps each feature map onto another feature map. The third layer is a convolutional layer that generates high-resolution images based on non-linearly mapped feature maps. I used ReLU as an activation function, and the filter size and number were implemented as written in the paper. This is a picture of training the SRCNN model. I used 1000 low-resolution images as training data from Kaggle and used set5 dataset as test data. The set5 dataset is a dataset consisting of 5 images commonly used for testing performance of image super resolution models. The picture on the left is the original low-resolution image, and the picture on the right is the output image of SRCNN. It can be confirmed that the image quality has improved. Next, I implemented the FSRCNN model. This is an optimized model from SRCNN. Unlike SRCNN, low-resolution images were not upscaled by interpolation and used as input. The image was put into the network as it is, and its size was increased by the convolutional layer. Unlike SRCNN, interpolation is not performed, so the amount of calculation is reduced. The first layer is a convolutional layer that extracts features, and the second layer is a convolutional layer that reduces feature dimensions called shrinking layer. The amount of computation is reduced because the number of parameters to be learned is reduced by reducing the feature dimension. The third layer is a convolutional layer that non-linearly maps feature maps to other feature maps. The fourth layer is a convolutional layer that expands the feature maps. It has the opposite function of the shrinking layer. The fifth layer is a convolutional layer that generates high-resolution images by transposed convolution. I used prelu as activation function. This is a picture of training the FSRCNN model. I trained and tested with the same data as SRCNN, and you can see that the learning time is greatly reduced. The picture on the left is the original low-resolution image, and the picture on the right is the output image of FSR CNN. Although the image quality has improved, you can see that the performance is slightly lower than that of SR-CNN. Finally, I implemented EDSR. When learning a deep network, the filter parameters may not be learned properly because of the gradient vanishing or the gradient exploding. To solve this problem, a residual learning method appeared and EDSR was designed to build a network using it. The network is deep and wide, resulting in a very large number of parameters. In order to stably learn the deepened network, the network is divided into residual blocks and each is connected with a skip connection to optimize the filter parameters. This is a picture of showing the structure of EDSR. You can see that the network is very deep. A total of 36 REST blocks were used and the number of channels increased by more than 4 times compared to other existing networks. And the number of parameters were also increased significantly. 800 div2k trained dataset images were randomly rotated and flipped to train, and step 5 dataset was tested for benchmarking. Compared to SR-CNN and FSR-CNN, you can see that the learning time is greatly increased. The picture on the left is the original low-resolution image, and the picture on the right is the output image of EDSR. Compared to SR-CNN and FSR-CNN, you can see that the performance is significantly improved. I will conclude the presentation by comparing the output with the 3 models described above and the AI-based super resolution service currently in service. The photo above is the original photo of Hongik University, and I made low-resolution images by downsampling. Upscale Media is an AI-powered tool that automatically upscales images. All 3 models improve image quality slightly, but there is distortion. In my opinion, this is a problem that inevitably arises because it is a nilpost inverse problem for which the correct answer has not been decided. The performance of the upscale media is much better, but I think this is due to the use of improved models that have appeared since the EDSR.